We're now in the home stretch. We just need to evaluate this third surface integral, which is over this top part of our little chopped cylinder right over here. So let's try to think of a parameterization. And let me just copy and paste this entire drawing just so that I can use it down below as we parameterize it. So let me copy it, copy, and then go all the way down here and let me paste it. Let me paste it. OK, that is our shape again, our surface. And then let me go to the layer that I wanted to get on. And then let's start evaluating it. So what we want to care about is the integral over surface 3 of z ds. And surface 3 here, we see that the x and y values essentially take on all of the possible x and y values inside of the unit circle, including the boundary. And then the z values are going to be a function of the x values. We know that this plane, that this top surface right over here, S3, it is a subset of the plane z is equal to 1 minus x. It's a subset that's kind of above the unit circle in the xy plane, or kind of the subset that intersects with our cylinder and kind of chops it. So let's think about x and y's first. So x, let's think about it in terms of polar coordinates, because that's probably the easiest way to think about it. I'm going to redraw kind of a top view. So I'm going to redraw a top view. So that is my y-axis, and this is my x-axis. And the x's and y's can take on any value. They essentially have to fill the unit circle. So if you were to kind of project this top surface down onto the xy plane, you would get this orange surface, that bottom surface, which looked like this. It was essentially the unit circle, just like that. Let me draw it a little bit neater than that. I can do a better job. So let me draw the unit circle as neatly as I can. So there's my unit circle. And so we can have one parameter. We can have one parameter that essentially says how far around the unit circle we're going. So that would be our angle. And let's use theta, because that's, well, just for fun. We haven't used theta as a parameter yet. That's theta. But if we had x's and y's as just a function of theta and we had a fixed radius, that would essentially just give us the points on the outside of the unit circle. But we need to be able to have all of the x, y's that are outside and inside the unit circle. So we actually have to have two parameters. We need to not only vary this angle, but we also need to vary the radius. So we would want to trace out the outside of that unit circle, and maybe we'd want to shorten it a little bit, and then trace it out again, and then shorten it some more, and then trace it out again. And so you want to actually have a variable radius as well. And so you could have how far out you're going. You could call that r. So for example, if r is fixed and you change your ranges of theta, then you would essentially get all of those points right over there. And you would do that for all of the r's, and from r0 all the way to r1, and you would essentially fill up the entire unit circle. And so let's do that. So r is going to go between 0 and 1. R is going to be between 0 and 1. And our theta is going to go all the way around. So our theta is going to go between 0 and 2 pi. Let me write this down. I wrote 0 instead of theta. Our theta is going to be greater than or equal to 0, less than or equal to 2 pi. And now we're ready to parameterize it. X of r and theta is going to be equal to, so whatever r is, it's going to be r cosine theta. So x is going to be r cosine theta. Y is going to be r sine theta. That's going to be the y value, r sine theta. And now z is essentially just a function of x. Z is going to be equal to 1 minus x, but x is just r cosine theta. So there you have it. We have our parameterization of this surface right over here. The x's and y's can take all the values of the unit circle, but then the z is up here based on a function of, well, really on a function of x. It's 1 minus x. And so that will give us all of the possible points right over here on the surface. You pick an x and y, and then the z is going to pop us right here someplace on that surface. And we can write it as a position vector function. Instead of calling that position vector function r, since we've already used r for radius, I will call it, I don't know, let's call it, I'm just going to pick a random letter here. Let's call it p for position vector function. And so p, our surface p, we can write it as, actually, no, I just call it surface 3. So surface 3 surface 3, I'll do it in that same purple color too, just so we know we're talking about this. Surface 3 as a position vector function, as a function of theta and r. Maybe I'll write r and theta, because that's how I think of things. R and theta is going to be equal to r cosine theta I plus r sine of theta j plus 1 minus r cosine theta. Need to get some real estate here. 1 minus r cosine of theta k. 1 minus r cosine of theta k. And now we are ready to start doing all of the business of evaluating the actual surface integral. So the first thing we need to do is take the cross product of this, the partial of this with respect to r, and the partial of this with respect to theta. And so let's just get down to business. Let's take the cross product. Let's take the cross product. And so we have our I unit vector, we have our j unit vector, and we have our k unit vector. And this might get a little bit involved, but we'll try our best to just work through it. Give myself a little bit more space. And so the partial of this with respect to r. So let's take the partial of this with respect to r. I'll do it in blue. The partial of this with respect to r. The partial of this with respect to r is just cosine theta I. So this is just cosine theta. I said I was going to do it in blue, and that's not blue. So this is going to be cosine theta. The partial of this with respect to r is sine theta. And the partial of this term right over here with respect to r is negative cosine theta. Negative cosine theta. Now let's take the partial with respect to theta. The partial of this with respect to theta is negative r sine of theta. Negative r sine of theta. The partial of this with respect to theta is r cosine theta. R cosine theta. And the partial here, this is 0, and then this would be negative r sine theta. Negative r, oh no, let me be careful. This is going to be, you have a negative r, so the derivative of cosine theta with respect to theta is negative sine theta. So the negatives are going to cancel out, and so you're going to have r sine theta. And now we can actually evaluate this determinant to figure out the cross product of the partial of this with respect to r and the partial of this with respect to theta. I'm not writing it down just to kind of save some real estate here. And so we have, actually maybe I will write it down just to be clear what we're doing. The partial of S3 with respect to r crossed with the partial of S3 with respect to theta is equal to, now our I component is going to be sine theta times r sine theta. So that's going to be r sine squared theta minus r cosine theta times negative cosine theta. So that's plus r cosine squared theta. All of that times I, and a simplification might be popping out here at you. And then you have minus the j component. The j component is going to be cosine theta times r sine theta. So it's r cosine theta sine theta. And then we're going to subtract from that. See, the negative signs cancel out. So you're going to subtract r sine theta cosine theta, or r cosine theta sine theta. Well, this is interesting because these are the negatives of each other. R cosine theta sine theta minus r cosine theta sine theta. This just evaluates to 0. So we have no j component. And then finally, for our k component, we have cosine theta times r cosine theta. So we have r cosine squared theta minus r sine theta times sine theta. So, or minus negative r sine theta times sine theta. So this would give you a negative, but we're going to have to subtract it, so it gives you a positive. So plus r sine squared theta k. And so this simplifies quite nicely, because this is going to be equal to, this term up here, you can factor out an r. This is r times sine squared theta plus cosine squared theta, which is just, that part simplifies to 1. So that's just r times I. So this is equal to r times I. And we do the same thing over here. This also simplifies. This is actually the same thing. This also simplifies to r. So this whole thing simplifies. Let me write it this way. This is also r sine squared theta plus cosine squared theta, also simplifies to r. So you have r times k. And so if you want the magnitude of this business, so let me make it clear. So the magnitude, we'll go back to the magenta. The magnitude of, I don't feel like rewriting it all. I'll just copy and paste it. Edit, copy, and paste. The magnitude of all of this business is going to be equal to the square root of this squared, which is r squared, plus this squared, which is r squared, which simplifies to, this is 2r squared. So you take the square root of both of those, you get the square root of 2 times r. So this is equal to the square root of 2 times, it would be the absolute value of r, but we know that r only takes on positive values. R only takes on positive values, so it's the square root of 2 times r, which is very nice because now we can evaluate ds. ds is going to be this business times dr d theta. So let's do it. So our surface integral, the thing that we were dealing with from the beginning, that thing right over there. So our surface integral, the surface S3 of z ds is now equal to, so I'm going to use different colors for the different variables of integration. So 1 on the outside, and then I'll do 1 on the inside. I'll do the inside one in pink. Z is equal to 1 minus r cosine theta. So z is equal to 1 minus r cosine theta. It involves both, so I'll use a different color. Minus r cosine theta. And then I just have to integrate relative to both of the variables. 1 minus r cosine theta. Oh, no, I have to do the times ds. ds is this thing. It's this thing times d theta dr. So let's see. Let's write this down. Times square root of 2r. So let's write that down. So that's times the square root of 2r times the square root of 2. And we can write the square root of 2 out front since it's a constant. So let me just do that. It simplifies things. Square root of 2 times r. And now d theta dr. Or we could write dr d theta. Either way. So let's do that. Let's do dr d theta. So dr d theta. We could do it either way. It's going to be about the same level of complexity. And so first we're going to integrate with respect to r. And let me do the colors the same way, actually. So dr d theta. d theta. If I've got colors, I might as well use them. And actually, I just realized that I'm way out of time. So actually, let me continue this in the next video. We'll set up the boundaries of integration and then just evaluate it.